Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Cordelia Latham and Julia Kamenetzky with us today.
Hello.
Hello.
Hi.
Hello, Cordelia. And let's start with Cordelia. Cordelia, where are you located at? What's your geolocation?
I'm located in Salt Lake City, Utah. I currently go to the University of Utah. I'm a grad student in a PhD mechanical engineering program now.
Wow, very cool. So you're doing two degrees?
Nope, just the PhD.
Just a PhD. Okay.
Yeah.
Very cool. Very cool. And so in your first year?
Yep.
Very nice. Very good. Good luck with that. Hope it all works well and goes super well.
Thanks.
And Julia, where are you at?
I am also in Salt Lake City, Utah. I'm an associate professor of physics at Westminster University, formerly Westminster College. And so I'm just right down the road from University of Utah.
Very good. And I'm in Phoenix on this June 14th, 2023, as we record this. And amazingly enough, in Phoenix in mid-June, the power switch has not been hit yet. We are still relatively cool for June. So, and is summer on the way in Salt Lake City, Utah? Thereabouts.
It's been pretty nice.
Like
it hasn't gotten too hot yet either.
Right.
Yep.
Yeah. No climate change here. That'd be very good. Super. And Cordelia, what do you like to do for research? Current or past?
Past, I really liked astrophysics. I enjoyed basically what this paper's on, studying stars and their distance and things like that. Currently, I work in a research lab where I 3D print microscopic sensors.
Oh, very nice.
Hopefully we'll eventually have a use for different instances that I can't share a whole lot about, but
Proprietary.
Yeah, so far it's been really good.
All good. Very cool. Very cool. And Julia, what do you like to do for research?
Well, my PhD work and my postdoctoral work was in sub-millimeter spectroscopy of mostly nearby galaxies and studying the cool molecular gas.
Yep.
That is that link towards star formation. Since coming to Westminster, I've really kind of pivoted to any kind of projects that I can involve undergraduate students on in meaningful ways. So I've studied light pollution, characterization, variable star monitoring, worked with some exoplanets, and getting really excited for the 2024 total solar eclipse and studying the solar corona.
Very nice. Very nice. Very cool. Very good. And that is going to bring us to this very awesome research note. It's open access, people. You can go get a copy for free. Go grab one. And an estimate of the distance to AN/SUR using RR Lyrae period, luminosity relationship. And Cordelia and Julia, take us away.
All right. Well, first I wanted to give a shout out to Michael Fitzgerald. My apologies. He was in charge of our solar siblings and helped give us access to Las Cumbres Observatory to make this whole research project possible, which I'm very grateful for.
Thank you, Michael.
And then we'll head down to the introduction. I don't want to give everything away in the abstract.
No, we don't want to give away the marbles yet.
Okay.
Right.
Wow. So our Lyrae stars have been used as standard candles as well as C-feed variables. So our Lyraes are evolved low mass stars and therefore have lower luminosities than C-feed variables, limiting their reach as distance indicators. But advanced methodology has increased the precision of our Lyraes as distance indicators, which are unable to be traced by C-feeds. So therefore, our Lyraes can trace older stellar populations, whereas C-feed variables cannot.
Fair enough.
We participated in a research program led by our solar siblings and Las Cumbres Observatory, the Global Sky Partner project, concentrated on getting students involved in scientific research.
Nice.
Where we observed AN/SUR for several weeks to determine its period and use the theoretical period luminosity relationship, which is cited in there, to determine the distance and compare our distance with Gaia's via stellar parallax.
There you go. Okay.
So onto the images. So images of AN/SUR were taken about every 2 to 4 hours. via LCO.
Wow.
The images were calibrated and cleaned using the R Solar Siblings pipeline. And as you can see, there were about 400 images. The data was analyzed using ExtraSource.
1, 2. Yep.
To determine apparent magnitudes in each band as a function of time and do Fourier decomposition. We corrected our average apparent magnitudes for interstellar reddening and calculated for the LCO band passes.
Okay.
We then determined the distance in parsecs to answer by comparing our average apparent magnitudes to the theoretical calculated absolute magnitude, and errors were propagated.
I'm with you. Yep. Very good. Well,
And then heading down.
and we have.
And there's all of our equations that we used in order to correct for interstellar reddening and get the magnitudes for the different bands.
And Z here is a metallicity. Yes, here we go.
Yes.
Okay. Okay. These are V band. These expressions are for V band. Okay, very good. I'm with you. Okay, and then for longer wavelengths. Okay.
Yep, for like the I and Z, and then there's that one.
Yes. And you propagate your arrows through there. Okay, I'm with you.
Great.
Okay.
Okay. And then to start out the results, I wanted to talk about figure 1, where figure 1 is a folded light curve of the IP band, apparent magnitude versus phase.
Yes.
And then if Julia wanted to talk more about it.
Sure, yeah. So when we are, getting our data from LCO, we don't necessarily get to choose exactly when those observations are going to be, but we request a certain cadence. So if you were to just look at our magnitude, as a function of time, it's every which way. And so we do the Fourier decomposition to figure out the period of the pulsation, and that's how we were able to get this decomposed or folded light curve. And if you notice, it's actually showing the same set of data twice, so that you can more easily see that up and down pattern. Right,
with a shift in color around a phase of 1. Okay. And so there would be 400 dots then on here. Is that right? 400 images.
Did we use the full, if we use the full set of images, then each color was going to have that many. Yeah.
Yeah, right. Okay, good. I'm with you. Yep. Okay. And reddening. What happened with reddening?
So we just have to correct for interstellar reddening. That correction is going to depend on the band pass and what wavelengths we're looking at. And so what we're able to get then are apparent magnitudes for each band. And of course, then the big comparison is to the absolute magnitudes predicted by theory.
Okay.
By comparing those two, we can get those distances.
Cool. I'm with you.
Do you want to take it from there, Cordelia?
I can. Should we mention the distance or should we keep it a secret?
I think we're there. Cat's out of the bag.
At some point, you're going to spill it. So, okay.
Okay, well, the apparent magnitude, the distance found via each band were 809 plus or minus 39 parsecs, and then 909 plus or minus 64, and 926 plus or minus 37. So the weighted average is 176 plus or minus 25 parsecs, which was not that close to Gaia, which was a bummer, but
Interesting though, right?
Agreed.
I mean, it's differences that make it interesting. If all you got was the exact same answer, I don't know if this research note would be here. Maybe it would.
Hopefully, but you're not wrong. So we learned throughout the year of writing this paper that there were 2 Gaia reports that we compared, or I guess a second one that came out right when we were getting ready to publish it.
Okay.
So we compared our distance to the DR2 and the DR3 reports.
Okay.
And I believe the DR2 was the 959 parsecs.
That one's later. That's
that?
from DR3.
Oh, I see. DR is 1052.
Right.
So then DR3 eventually like came closer to our value, which seemed promising. So maybe if there's like a DR4, it might match.
Hope springs eternal.
And Gaia gets these measurements via stellar parallax. And the distance is each getting lower and closer to our calculation, but not in all cases. The reddening correction slightly increases the discrepancies between our distances from each of the 3 bands.
Yeah, right.
So I think our distance could be lowered in the absolute magnitude. If it's too large, we already used the metallicity measurement, which resulted in the largest distance. Because if you notice in the next paragraph, a lot of the metallicity values are extremely small. Or I guess closer to 0.
Ooh, yes. Here we go. Yeah, 0.47 on FE over H. Okay. Got it. And that's from Gaia. Okay. DR3. Okay. Wow. So you need a very metal poor star.
Yeah.
if you want them out, if you take it at face value, you need a very small metal.
Yeah. That's why I corrected my wording. I said very small, and then I realized it needed to be smaller.
Indeed. Cool. Very good.
Then in the conclusion, which I guess I've kind of already pointed out, that there is a discrepancy between our measured distance and Gaia's. And this project demonstrated the successful use of distributed remote telescope networks like LCO for facilitating undergraduate research projects, which I am very happy to be a part of.
Awesome. Congratulations. It's very neat. Well, I'm going to save my questions till we get to the next one. But very good. Nice work. Beautiful work. Well done. So Cordelia and Julia, thank you so much for walking us through your very lovely research note.
Thank you.
Thank you.
And of course, this opens all kinds of questions, like where might the discrepancy come from? Is it something that could be solved with additional observations? Do we need to reconsider the theoretical models? How confident are we on those reddening values, etc.? And so where do we go from here trying to get these observations and DR3 to agree, or even DR2? So where do we go from here?
Yeah, like you said, it could be a lot of different things. I think that the way to go is to look at a more systematic analysis of when we compare the period luminosity relationship derived distances to the Gaia distances. How many of them can we develop a larger sample to tell us if these differences we're finding are systematic or not? As we mentioned in the paper, a few of the other students working in this Our Solar Siblings project found similar results, but not everyone. At this point, it's anecdata, but there's something that would be worth investigating. I would definitely be interested in updated theoretical models of horizontal branch stars, as well as I think some other folks are looking into more empirically derived relationships. And I'd love to see that comparison between the empirically derived relationships, if we're looking at the Gaia results, and the theoretical ones, and how do we bring those together? How do we figure out why the discrepancies are there and how to account for them?
Right. So has anybody else looked at this object, or are other people planning on looking at this object, or are you the first and so far only ones to look at this object?
Of this particular one, I think at least of the Our Solar Siblings group and the researchers they've been working with, I think we were the only one, but there are lots of other researchers looking at many different ones and finding different things. Okay.
Okay, off the wall stuff. Are we sure it's a single star?
Good question. I've worked with a few other students on a similar project like this, work that didn't get published, and one of theirs did turn out to likely be a double star, and that is, of course, then affecting what we're seeing. So I didn't see too much questioning that for this one.
Okay. Okay.
Yeah.
I mean, your light curve is very nice. You would have thought if you had any sort of a massive companion, you would have seen additional modulations in that curve. So
Yeah.
interesting. Very cool. Well, I certainly look forward to seeing this one get resolved over the next 10 years, whatever that may be, a couple of years. Usually when there's a discrepancy, you get all kinds of people coming after it. Oh, why is that? Why is that? So
Yeah.
it'd be very fun to see this resolved over the next couple of years. It'd be great.
I agree.
All righty. Well, Cordelia and Julia, thank you so much again for walking us through your very lovely research note.
Thanks
you.
for having us.
Yeah.
And I hope this made your astronomy day just a little bit better, everyone. And we will see you on the next one. Bye-bye.